more discussion later on. So we have one more talk. Leon Alkalai, also at JPL, is going to be looking forward to the future and opportunities for future lunar missions.
My name is Leon Alkalai, and I want to thank you all for staying for the last presentation. So, frankly, I did not pick the title for this. Somehow the organizers did. It's a huge topic, plans and opportunities. So I'm going to just try and address that partially and discuss some of the work that I've been doing. Over the past 10 years, I've been working at JPL on almost exclusively lunar robotic mission formulation. And so I'll present some of those results and some of the ideas and outlook for the future. I'll explain this picture at the end, but you can kind of enjoy it for a moment, and then I will conclude actually with this vision of what it is a lunar robotic village that I'm eager to advocate. So before we get there, let me kind of give you a little bit of an introduction. So I've been fortunate to work at JPL on a number of lunar mission concepts. I've been part of the mission formulation, solar system mission formulation program office. Brent Sherwood is here in the audience, and Kim Ray was here earlier today. Both of them are in the same program office, and we've been working on a number of these mission concepts together for a number of years. I first got into the business about 10 years ago with a mission concept called Moonlight. In fact, I have a lot to credit Goddard Space Flight Center for getting me into this business. It was about 10 years ago that Maria Zuber from MIT and Dave Smith from Goddard had planned to do a lunar mission. They had a very ambitious concept to do a high-resolution mapping of the moon and use optical communication to get all the data back from the moon. And they went to Al Diaz at the Goddard, who was the center director. And in 2003, just so you know, Al Diaz told them that Goddard is not in the lunar business and that they should go to JPL. So that's what they did. They called Charles Elachi. Charles Elachi welcomed them. And I was in a career transition. I was actually looking to change careers at JPL from a technology development career. And I was interested in doing mission concepts. So I interviewed with Maria Zuber, and I told her I've never done anything like this before, and she said, "You're it." And so that was my beginning, and this was proposed to Discovery 10 competition. If you recall, Discovery 10 did not pick a mission concept for implementation, but they did pick a mission of opportunity, which was M-Cube. So that was a very interesting experience, a lot of exciting work with working closely with Maria Zuber and Dave Smith and others. After that, we proposed Grail, and so I was the proposal manager and later what we call capture lead for Grail. I consider it very successful both from a formulation point of view and certainly from a science point of view. And then in the period of 2005 to 2012, we worked on Moonrise, and we're still working on Moonrise, and Barbara Cohen is here as a co-I on Moonrise. Mike Duke was the PI in 2005, and then he retired, and Brad Jolliffe, who was the deputy PI, is now the PI for Moonrise, which was proposed in the New Frontiers, both 2 and 3. So it was not selected for implementation, but it completed both times a Phase A study, which means both times it was in the finals of the competition. In parallel to Grail, and I'll describe this in more detail, I was working on a mission concept called Lunette. And Lunette is a mission concept to send a network of landers to the moon, and I'll describe that a little bit better. This was also proposed last discovery round by Clive Neal as a discovery proposal. At the same time that LCROSS was competing for the impactor mission, JPL had a lunar impactor proposal, and we were in the finals competing with LCROSS, and LCROSS beat JPL in this competition and did a good job of implementing the mission. But we had our own impactor that was based on an ESPA ring that we were proposing as a mission concept. That was in 2006. And finally, I'll describe a little bit more another study that we did, and this one is perhaps the most relevant to this workshop, a study called Miranda. Miranda, which I always forget what the acronym is, but it's in one of the charts. It is a mission concept where we wanted to determine not only the presence in situ, but the abundance of water on the moon. So there was a clear need to do long-term traversal and reaching into deep craters, cold traps, and so on. So we put together a mission concept to do that. So these are just some of the highlights. This does not complete the full picture of all the mission concepts we've been working on over the past 10 years. And I'm sure I left out something, but I kind of went through a further list of different mission concepts and different capabilities that we've been looking at. We've been spending a lot of resources on just sample acquisition and transfer systems. This particularly is applicable to a Moonrise kind of a mission. Moonrise is a sample return from the South Pole Aitken Basin. So a lot of capability went into developing a end effector, a robotic arm, and a scoop to sieve and collect samples. We've been looking at various a suite of landers, small landers, large landers, hard landers, soft landing, powered descent, hazard avoidance, nuclear-powered landers, and rovers. We've been looking at subsurface accessibility through penetrators, drills, heat flow probes, surface mobility. We've been also looking at CubeSats. Rob mentioned CubeSats. We've been studying CubeSats for lunar exploration. In 2005, we published work on a gravity mapping CubeSat using corner-cube reflectors. And then we've been, it's pretty obvious that there's a huge international interest in lunar exploration. I've listed only some of the topics here that JPL's been involved with, and certainly other NASA centers have been doing a lot of work with international partners. There's been a mission concept called Moonlight that the UK Space Agency has been working on together with Surrey Space Systems to put an orbit around the moon and deploy probes, multiple probes that would plant a seismic sensor in a few meters under the surface of the moon. We've had a proposal with ESA and CNES and IPGP on a network of landers called Farside, with the Germans on Lunar Exploration Orbiter, and so on, working with the Indian Space Agency, the Canadians, the Russians, Japanese, and more recently the Koreans have shown a strong interest in going to the moon. They briefed JPL and Ames and Goddard just a few weeks ago. And I thought I'd list, not that anybody here needs reminding, but just in the last 10 years, and I hope I didn't leave out anything, but in 2003, let's not forget the ESA had the Smart 1 mission, then we had Chang'e, Selene, Chandrayaan, and with M-Cube and Minisar, LRO, LCROSS, and so on, Grail, and I put here LADI with all the best of luck on September 6th. So there's been a lot of activity at the moon, and certainly a lot to show for it, a lot of good science at the moon. So let me just go through some of those mission concepts that we've been working on over the year, including Grail, and then I'll finish with some forward-looking mission concepts. So Grail, it was actually quite a big win for the lunar community and certainly for JPL and MIT and Goddard, in the sense that it was clearly not a front runner or a likely winner in the discovery competition. It was not at all evident that a single focused science measurement of gravity at the moon would rise to the occasion of being selected for a discovery competition. So we're very happy that that threshold of achieving science, the discovery science, was achieved through Grail. Grail was remarkable in many ways. It actually took the mission concept from the mission called GRACE at the Earth, of measuring gravity around Earth, and kind of transplanting that mission concept from Earth to the moon. For the longest time, we couldn't come up with a creative name like Grail, and we did that in the last moment, and it was referred to as Grace at the Moon. And then a lot of heritage was also in the spacecraft. Lockheed Martin was able to use the XSS-11 spacecraft to do the science. So altogether, it used the mission concept that was demonstrated at Earth, the spacecraft that was also demonstrated at Earth, and there were additional capabilities to make sure that the gravity recovery can be done at the moon. But it was not at all a likely candidate to win. At the time, it was competing actually against OSIRIS-REx from Goddard and Vesper as well. Moving on, Moonrise is a lunar sample return mission concept at this point, or a proposal. It's already been through 2 phase A studies, and it's a mission to robotically go to the far side of the moon, to the South Pole Aitken Basin, land robotically. The critical events are being relayed through an orbiter, and spend the lunar day on the surface of the moon, sample up to a kilogram of rock fragments from the regolith, put it in a sample return capsule, and then bring the samples back to Earth. This has been already twice proposed in New Frontiers. Unfortunately, twice it has not been selected, but a lot of investment has been made in maturing the concept. In fact, JPL does have a very high fidelity testbed in place where we even have high fidelity simulations of the lighting conditions, a very high fidelity testbed with lunar regolith simulant down here. And this is a full-scale lunar lander. It's about over 6 feet tall, and this is a camera contributed by DLR, by Germany, stereo camera. This is the robotic arm. It can reach out over 2 meters, and this is the end effector that is able to scoop and sieve and collect rock fragments in a specific range that the science team wants to collect. Over here is a canister, so the samples are collected inside the canister. This capsule opens up, and the canister is transferred into the sample return capsule, and this is the ascent vehicle that's on top of the lander. The capability of this lunar lander is to deliver to the surface of the moon about a ton of payload. If you consider the ascent vehicle and the sample return capsule, everything that's on the lunar ascent vehicle as a potential payload, then the capability of this lunar lander is to deliver about 1,000 kilograms to the surface of the moon. This is something that certainly if Moonrise were to be selected by the New Frontiers program, that a follow-on mission or reuse of such a lander could deliver Jerry's ISRU unit easily with margin. This is just a little bit more detail. You can ignore these dates. This was from the last proposal. But this is a mission concept, the mission overview of Moonrise. It has the orbiter and it has the lander. It has a solid rocket motor to stage the braking burn, and then a powered descent. And it spends about 10 days on the surface of the moon, collects the samples, and then launches the ascent vehicle back to Earth. And there's the sample return capsule is deployed much like Genesis and Stardust. So this mission concept, as I said, has already been matured sufficiently. It's been through 2 phase A studies. I mentioned Lunette. I'm very excited about Lunette. Clive Neal is the PI for the latest Discovery proposal. But Lunette originated from the idea of sending a network of small landers to the surface of the moon. This shows one concept, but they're basically two different mission concepts. You can have a common stage that takes like an ESPA ring with multiple, let's say 6 small landers to a specific region of interest at the moon, and then above that region it deploys the 6 landers, and which only need to do a powered descent, but they have a common stage to do the braking burn. We've looked at that approach, and that may be applicable to, let's say, a region where you've identified the high likelihood of, let's say, polar volatiles, but you want to still have a local geographical network, so something like this would be applicable. On the other hand, to do more geophysical science, where you want these landers to be distributed on much larger regions, then each one of them has to have its own braking burn motor in order to go through to very different locations on the moon. So we've looked at both approaches, a regional network of small landers or a global network of small landers. We refer to both as Lunette. In this one of the mission concept, this is a design of a Lunette lander. Typically this lander would be of the, just so you know, the total mass, landed mass, dry mass would be about 120 to 150 kilograms, with a landed payload of about 20 kilograms. So just so you have a feeling for how much payload it might be able to deliver to the surface of the moon. This is the mission concept that we studied. Now I can read it. Moon Ice Resource Abundance and Natural Distribution Assessment, Miranda. This is a very exciting and interesting study that I said most, I think, applies perhaps to this workshop. We wanted to take the hypothetical that NASA selects Moonrise for a New Frontiers science mission, and then how can we use the same lander and the same capability for future missions to the moon. In this case, we took the Moonrise lander and we put a mobility system as part of the payload. So think of this as being part of the 1,000 kilograms that you can deliver to the moon. So this is, many of you would recognize the frame and the legs of an athlete robot. So these legs are basically folded up, and actually I think I may have it here. It's the same thing. So in this case, the legs are folded up, but the lander lands, and then upon landing, so it lands on these Moonrise lander legs, and upon landing, these athlete legs basically unfold, and the secondary mobility system stands up, lifts itself up, and drives away from this lander. And it's designed, the mission concept was to land close to, let's say, a crater where it would be too dangerous for a lander to land too close. So this could be kilometers away from a crater where you may think or expect there to be volatiles. And then this robotic system would drive kilometers away to the edge of the crater, and then it would deploy, some of you may know about the Axel robotic system. So there would be these two robotic tethered vehicles that can be deployed, and they can actually go down deep into a crater. They have a sampling system within the robotic system, and then they sample and they can bring it back to the lander for analysis and so on. We were particularly interested in analyzing the capabilities from the point of view that the science community would want to go to many different locations to sample, not just one or a few or a dozen, but many, meaning anything between 10 to 100 locations. We were generally concerned that any result from one or a few locations would not be a sampling, a large enough sampling to draw any meaningful scientific conclusions. So we were under the impression that a lander like this or a mobility system would have to traverse between 10 to 100 kilometers and go between a dozen to several dozen locations. So that's kind of what this was designed to do as a mission concept. And that's perhaps something that may be of interest to this workshop as we go along. Another mission concept that is more recent, and by the way, if I didn't mention, I apologize, but everything I'm presenting here today and all the pictures and all the material has been published. And at the end of the presentation, I have a list of papers that anybody who wants to look at it can see. So each one of these, there's papers behind each one of these if anybody's interested in learning more. Recently, we've been working on a mission concept called Orion-Moonrise, first at JPL alone, and now in the past year together with Lockheed Martin. This mission concept, again, looks at Moonrise, the future of Moonrise in terms of if NASA were to pick a lander after Moonrise is selected, or perhaps if NASA decides to do a directed mission where a Moonrise vehicle would land on the surface, and rather than returning samples back to Earth, would return samples to the Orion vehicle, which would be possibly in the Earth-Moon L2 orbit. So this was designed to be a combination of robotic and human exploration, and this is a mission concept we pitched to both SMD and HEOMD. Yes? Very good question, and thank you for that question. So the question is, do I need to use the full 1,000 kilogram? So we've done a few things with a difference. So clearly you don't need to. One thing that we made that is a huge windfall, because you don't need the structure for the sample return capsule, we basically said how much more samples can you bring to the EL2 instead of 1 kilogram as New Frontiers required. So we did the math and the analysis, and it turned out to be somewhere around 38 kilograms of samples. Well, that's a big deal for the science community. Instead of 1 kilogram, if you can return 30 kilograms via the Orion, that's a big deal. The other thing that we were able to add here from a capability point of view is a rover. So we added to the lander a rover, but a small-scale rover. It was of the order 50 kilogram or so. But that still left some margin to play with. So this is just a mission concept in a normal bat chart as we would show it. So in this concept, the Moonrise lander and the crew on Orion are launched separately. We actually did a lot of trade studies here to see if they can launch on the same launch vehicle, on SLS, and so on. But just to make things simpler, we decided to launch them separately. So here's Moonrise, here's the Orion. And so Moonrise would launch before the crew and get staged in a staging orbit, in this case at L1, and just wait for the crew. In this case, this is an older version. We weren't sure whether there would be a human habitat at that place or not. It doesn't matter. There could be, or there doesn't have to be a human habitat. And in the latest paper we published, there is no human habitat, and the crew in Orion just goes into Earth-Moon L2. And then once the astronauts are ready, they basically give the go-ahead, and Moonrise, the sample return vehicle, then is staged, goes from the staging orbit and descends into the South Pole Aitken Basin. The nice thing is that the astronauts on board Orion have quite an exciting kind of set of tasks to do. They can perform the critical relay functions for the landing, and then they actually can do teleoperations on the surface of the moon while the robotic arm is sampling. They can also provide the critical coverage for the ascent, and then actually perform the rendezvous and docking and capturing of the sample canister and bring it back to Earth. At the next League meeting, which is coming up in October, we're presenting some new results on how exactly Orion would capture the samples and so on. This looks terribly out of place, but you'll see that it's kind of not out of place. InSight is the latest discovery competition that won. The nice thing about it, what's relevant to lunar exploration, is a lot of these payloads were the same payloads that were planned for Lunette. This is the seismic station from IPGP with Philippe Lognonnet. This is the HP Cube heat flow probe from DLR. And InSight, which is the next Mars mission going in 2016, it's a discovery mission going to Mars. The nice thing about this mission, if this is going to work while I'm talking, is that this animation shows how InSight is planning to deploy the instruments on the surface of Mars. So here you see the seismic station. It's just a kind of a model representation of it, and you see the top hat that goes on top of the seismic station, and then later you'll see the heat flow probe. But this is a very sophisticated and pretty involved system of robotic deployment of scientific payloads on the surface of another planetary body. It's quite challenging. Now InSight is going through its final stages of the phase B. So there's a PDR season going on right now with a PDR scheduled for mid-August. But this is involves scientific tethers for both the seismic instrument and the heat flow probe. And it involves a large set of activities to do precision deployment of scientific instruments on the surface, in this case of Mars. It's a first time that anything of this sophistication is being done in terms of payload deployment on any planetary body. So a lot of these results, a lot of this experience will, in my opinion at least, be very much applicable to lunar exploration as well. So this was the deployment, a two-step deployment of the seismic station, and you see the heat flow probe very uncomfortably close to the seismic station. That must have been a constraint in the animation. So this is, but it's a capability that clearly, as I said, is applicable to lunar missions as well. I thought I'd put in a page here that some of you may be following. NASA just issued an RFI, a few weeks ago maybe, recently, asking the commercial industry primarily on any information on commercial landers for lunar landers. And I thought I'd just give a little collage here of there's the work going on at JSC, at Marshall and APL, at Ames, and at JPL on different lunar lander concepts. They each have their different origins. Certainly each have their merits and capabilities, but I thought I'd list that certainly JPL is not the only place working on lunar landers. Ames has been doing a lot of work, as have other NASA centers. Then I thought I'd pay tribute to the Google X Prize competition. There's at least, that I know of, half a dozen or more commercial small businesses out there competing for the Google X Prize. At least a year or two ago, that number was about 20. I think it most likely is down a bit. But there's most likely only a few, maybe a handful, 4 or 5 mission or companies that actually have funding and are making significant progress. But this competition still stands, a $30 million competition for the Google X Prize to land on the moon and have a rover that will rove, I believe, 500 meters or something of that sort, take pictures. There's a bonus if they image a Apollo landing site and things of that sort. So this is going on, and I actually was at this opening ceremony, as was officially NASA headquarters during this opening ceremony. So this is still going on, and I think some of the earliest launches are being scheduled as early as 2015. I don't think any sooner. But it's a very tough thing to do. The $30 million doesn't nearly pay for the full cost of the development. So they clearly have to have other business models to justify the mission. So finally, I said I'd leave you with a justification for this nice rendering, at least an artistic rendering. So I just want to share with you, this is something I presented at the League meeting in 2010 as my personal vision of the future. This is not endorsed by anybody, and certainly not by NASA or JPL, but it's my personal view and vision of there being a robotic village, as I call it, or a colony of robotic systems on the moon as a precursor to human settlement of the moon. So given that there are so many international agencies planning and going to the moon, bringing samples or landers, orbiters, and so on, I believe it would serve NASA very well and serve the world very well if NASA would take a leadership role in building an actual destination, a location where the international robotic systems could actually land. This is kind of a pad, a notional pad, where they would actually land and build power stations, solar plants, do some actual development, in situ resource utilization, as Jerry knows. And anybody who has most probably a robotic system on the internet is somewhere in here. So you see the robonauts and so on. So I believe robotic systems can be used today very effectively to build shelters, to build roads, to interoperate and exchange tools and exchange capabilities. And something like this would, in my opinion, be extremely motivational. It would advance technology, and it would build habitats for future human exploration. So with that vision, I thank you very much for your attention.